Okay, so we're gonna wrap up chapter two. Does anyone know what this reference came from? I think it used when I was taking this class, everyone knew what this was, but I think at your age, no one knows what this is about. Anyone? You can raise your hand if you know. Really? Heaven knows? Cool. All right. This is from a stupid movie called Spinal Tap. I think it's in the early '90s, and the joke is that um, I think one of the musician, oh, he got a new amplifier for like 3 times the price, but then the knob goes to 11 instead of just 10, so it's much better because you can turn it up to 11. Okay, and because this amplifier can go up to 11, it must be louder than going up to 10, right? Where these, little marks are just arbitrary paint, right, on a box. It's just a really fun movie. If you haven't seen it, I think it's on YouTube. You can actually just watch it on YouTube. Yeah. So it's a really, really fun movie, and you know, and those of you who are musicians, we're not trying to make fun of you. It's just a fun music thing. You can do the same thing with other professions also. Okay. Okay. From this little picture here, we're going to talk about this idea of gain. Gain, right? Basically means if you have an input to something, right? Let's say I send a little signal. Let's say I send like a 1 volt signal in here as an input, right? Can I get an output that's different, right? See, you can either make it smaller, right, where the gain is now less than 1, or you can make it twice as big, right? So depending on how big the output is, right, that actually determines what the gain is, okay? And we're going to talk a little bit more detail about this. So let me show you an example that we already know, right? This voltage divider that you guys are playing around with on lab 1, right? We did a little calculation, right, using just Ohm's law and Kirchhoff's law, where you can calculate, right, if you have, let's say, some input voltage here, V in, right, it could be 10 volts, 5 volts, 2 volts, whatever that is, right, the output, right, is going to be some ratio R2 over R2 plus R1. Remember just doing the little Ohm's law thing? Okay. So this little number here is technically actually the gain of that circuit. It's less than 1, right, because R2 is going to be less than R2 plus R1, right, since resistors are always positive number. Okay. So the ratio between input and output is known as gain. Okay. So if you input 1 volt and you get 10 volts out, right, that means you have a gain of 10. If you input 1 volt, you get half a volt out, that means you have a gain of 1/2, right? Whatever that number is. Does that make sense what gain means? Okay, right? Basically, you know, this this thing is supposed to give you a big gain, right? Where turning it down to 1 maybe it gives you a small gain. Okay, and that's sort of the idea, and you can see how this will be useful, right? Basically, all your volume knobs, whenever you click on volume on your phone, or the brightness on your screen, the dimmer on lights, what you're adjusting is actually the gain, because you're supplying the same voltage to the input, but it's giving the light a slightly different output in order to dim the light, make the volume lower, make your screen brighter and stuff like that. Okay. Okay. What we're going to do is going to generalize this for both DC and AC circuits, okay, as opposed to just dealing with resistors, okay? And so thinking about them in terms of resistors, the thing we introduced yesterday, not yesterday, on Monday, was this idea of impedance, right? Remember the Z represents impedance, okay? Right? The impedance for a resistor is just a resistance. Impedance for a capacitor is 1 over J omega C. Impedance for an inductor is just J omega L. Okay, you don't have to memorize all this stuff, but but it's just good to kind of have that idea in your head that different things have different impedances. Okay, and some of these impedance depends on omega, which is actually the angular frequency, which is how fast that AC signal is coming in. And this is where we can actually do a lot of fun stuff with it. Okay. So this component box here, right, just this box here, has some impedance Z1, and this second box here, it could be a resistor, it could be a capacitor, it could be a semiconductor, it could be a monitor, it could be whatever, right? Some device has some impedance Z2, right? And you can actually apply the same equation as up here, where you just replace all the R's with Z's, right? And you will get the same result where the output, oops, right? These impedances, right, is basically just the voltage. Let me rewrite this, okay? Voltage as the function of time equals to whatever the impedance of that component is. It could be resistor, capacitor, inductor, some other device, times, right, the current, right? This is what I call generalized Ohm's law, right? Where if this was a resistor, V equals IR, right? This was a capacitor, then V equals I times the impedance of a capacitor, right? Right? And this is nice because now we just have to have one equation to remember, right? Z equals some impedance times the current. That's always going to be the case, okay? So in general, what will happen is that the output is going to be proportional to the gain, which also could depend on the frequency of the signal, okay? Because in this case, right, in this case where Z, I'm going to do it for the capacitor. Let's say both of these things are capacitors, right, C1 and C2, okay? Right? Instead of R1 over R1 plus R2, right, it goes to basically whatever the impedance of a capacitor is over the impedance of capacitor 2, capacitor 1 plus the impedance of capacitor 2, right? And then if you fill this algebra out, it just turns into this long equation, right? I'm not going to do that, but that's the same idea where you're just replacing, when you have two things, you have current just running along it, right? You can always use this voltage divider, right? But it's no longer dividing voltage, right? If you put a capacitor there, it'll be slightly different. If you put an inductor there, it'll behave slightly different, okay? But the main idea is that, right, if you have some input, okay, you multiply that by the gain, you get the output, whatever that is, okay? And that's the most important thing, okay? Just this idea of gain, okay, which represented by this big um, letter, big G, and there could be some dependence on frequency because, right, resistor doesn't depend on frequency, but capacitor does, inductor does, other devices also do that, okay? Right. This brings up to a sort of an interesting idea where what we're going to do is we're going to actually study this in quite a lot more detail in chapter 3 when we go into the frequency domains of AC circuit, which is what we're going to talk about next Wednesday, actually. Okay. But I'm going to follow the order of the book, even though I think this little section actually probably depends on, would be better if it was placed in chapter 3, but I just want to follow the order of the book so when you guys are reading it, you don't have to flip back and forth or actually scroll up and down, right? Okay. And this is the what's called the Bott plot. Okay. Bott plot is a way to basically characterize the gain of a circuit as a function of the frequency. Basically trying to figure out what this G as a function of omega is. Okay? And then if, I was in charge of the whole universe, right, I would just plot G as a function of omega, right? Because that's what a function is. But I'm not the emperor of the universe, but you guys can help change that if you want, right? um, this guy, Alexander Graham Bell, anyone remember what is he famous for? The telephone, yeah, inventing the telephone. And also, I think, isn't AT&T started by him? Or is it Pacific Bell or something like that? Yeah, all the Bell companies started by him. But I think AT&T swallowed them already. Yeah, but, okay, and we're going to run into this guy. So what he decided to do is actually not to plot G as a function of omega, is to plot 20 times dB, and dB stands for decibel. Those of you who had, remember the sound part in general physics, it rings a bell, right? And then it's the 10 base log of the gain. Okay, there's something funky on the left-hand side. Okay, on the right-hand side is the log of the frequency. Remember that regular frequency is related to angular frequency by this factor 2 pi. Okay. Okay. And it's like, why are we doing this? Okay, this is ridiculous. Even though you have omega on this side, you put f on the other side. You're just effing with us, right? It's not my fault. Okay, that's all I can say. Okay. And these plots will typically look like this, where you have, on the vertical axis, this crazy number, 20 dB log, and then G and stuff like that, right? On the right-hand side, you have log of the frequency, okay? And I guess there is a point to this. This is really nice to look at, okay? And we're going to discuss this in chapter 3, why these things called 3 dB points are very useful, and then, you know, where the characteristic frequency is actually very useful. But let's just save that for next week, because all I wanted you guys to do is actually kind of get a sense of what this plot is trying to tell us. Okay, so as I said, dB, the B here stands for bell, right? And then deci means 1/10 in SI units, right, or prefix, SI prefix, right? So I took a picture of Alexander Graham Bell and took a tenth of it, okay, and that's what that means, okay? Okay. So let me just give you guys the history of this. I think the book discussed this also. So Alexander Graham Bell was trying to figure out, okay, if I have a telephone here and I want to send a signal across the Atlantic to talk to someone in France, I think in France, right? Or actually probably in Portugal, right? How strong of a signal do I have to send it in order to power the telephone on the other side? So he was concerned with power, not voltage, okay? And remember, power, right, is the current times the voltage, right? And then if you just use kind of some sort of, you know, you use Ohm's law, you can actually replace this, right? This is going to be I divided by V over R. Get rid of this I, right? That means it's going to be V squared over R, right? So basically power is proportional to the voltage square, right? Where 1 over R is basically, you know, how long that damn cable is you have to run across the Atlantic, right? So power is proportional to the voltage square on some resistive, you know, on some cable. So that's what he's actually concerned with, okay? In order to figure out how strong the signal is going to be by the time it reaches across the Atlantic, he came up with this a number called attenuation. Attenuation. I think there's no second T there. No, third T. Attenuation. Okay? Basically, how much power loss there is once you send your signal across the Atlantic or across some wire or whatever that is. Okay? Okay. Since power is proportional to the voltage square, right? Whatever that is has to be proportional to the output voltage divided by the input voltage, but there's a square involved because of this relationship between power and voltage. Okay? At least now you know where this 2 comes from, right? Okay. Right? And a lot of times what happens is that when you're sending the signal, you have a very, very big signal. Let's say, I think the first telephone, it ran like at 150 volts in order for the input, right? And you send that signal across the Atlantic. By the time it gets across the Atlantic, it's like a tenth of a volt, okay? Because this long freaking cable you're dragging, long copper cable you're dragging across the Atlantic, okay? So you have to be able to see something that's a large number and a small number at the same time, right? Did they teach you how to see that in general physics? What kind of plot you should make for that? A log plot, right? Log plot allows you to see big things and small things on the same plot, okay? So that's why I took the 10 base log of it, okay? And that's what he called defined as attenuation, okay? All right, and then so since this is a log function, right? Remember one of the properties of log is that any power turns into just a multiplication, right? So you can actually bring this 2 down in front, so you have the log, 2 times log base 10 log V out over V in. That's exactly what the attenuation bell is, okay? And of course, V out over V in, we just talked about that, right? V out over V in, where did we see that before, right? V out over V in, right? Right? If you divide both sides of this by V in, right? That's basically gain, right? Okay? Right? The ratio of output divided by input, that's exactly what the gain of that circuit is, okay? And we're going to do an absolute value of it because there could be stuff that has negative gain, and then what will end up happening is that you try to take a log of a negative number, you punch on your calculator, you're going to blow up the calculator, right? Okay? You can't take a log of a negative number, Okay, we just need the absolute power. Okay, and the decibel, now we turn pink again. Okay, yeah, let's be pink for, let's try a different port so we're not pink anymore. Hold on a second. Cam. He said he fixed it. That's even pinker. How's that possible? It fixed it? Okay, great. All right. What was I talking about? Gain, right? Oh, yeah. And and then by some whatever reason, he also decided to multiply that number by 10. And hence, that's the decibel, okay? So instead of 2, you have a 20 here, okay? So a decibel is defined by 20 times log 10 of basically the gain, right? Absolute value, okay? And that's how this guy came up with, and then we're all suffering from it ever since then, okay? And that's because he wants to talk to someone in Portugal, okay? Just to punch in some numbers so you guys get a sense of what these numbers mean, right? If the gain of something is 1/100th, right? In decibel, it's actually negative 40. It's interesting, right? Because basically this power here is negative 2, right? It's 10 to the negative 2, right? 10 to the negative 2 times 20 is negative 40, right? Let me do another example here. If you have a gain of 1, unity gain, right? 10 to what power gives you 1? Anyone know? 10 to the 0, right? And then 0 times 20 is 0, right? If you have a gain of 10, right, the power is 1, right? 1 times 20 is 20, right? And that's how you kind of convert between the two, okay? So to me, this makes a lot of sense. This is harder for me to understand, right? But then, just think about what is the power if you take that power to 10 and then multiply by 20. That's how you get the decibel number, okay? Yeah. um, okay. Yeah. IN. Where? Which one? Scroll up. Oh, in decibel. Yeah, yeah. It's just they should have just put lowercase I, right? It's not natural log. Yeah, yeah. Sorry about that. Yeah, in decibel is that number. Okay, and this is what happens when you take the first draft of a textbook, right? So you get what you pay for. Okay, so that's what these plots will look like. So let me just describe what the values here are, right? Okay, so right, let's say the frequency of my signal is 1 hertz. Log of 1 is 0, right? So that's a very low frequency signal, right? And according to this plot, the gain is about, well, this this number here, right? I think it's above 0, so it actually has the gain of maybe like, sorry, it has a decibel number of maybe like 3, so it probably has a gain of like 1.44. Okay, so this is actually amplifying your signal. Whatever input you get is actually bigger than the output, right? But then it goes on and on and on and on, and it crosses 0, right, around here, right? And this is where what they call the kind of like the characteristic frequency, right? But then you take the log of it, so it turns into some funky number between 1.5 and 1.2, so it's like 1.675 or something like that. Okay, don't think about these numbers too much, but this is just how a lot of people look at plots when they're looking at these what's called the bot plot. Okay, you're plotting this funky number versus another funky number that you have to like disentangle in your head. Okay, and an example of this just to show you guys, people still use this, okay? So if you were to go to Texas Instruments website, so some of you guys probably have Texas Instrument calculators, right? Not only do they make calculators, they make a lot of computer chips and amplifiers, right? There's this chip called OPA 620. It's a fast amplifier that we use to amplify signal here, okay? And don't worry about what's in this drawing. We're going to learn all the stuff in a couple of weeks. Okay. The idea is that you put in some signal here, it makes the signal bigger, right? It turns it up to 11, okay, for you. Okay. And on the data sheet, what you will see is a bar plot like this. Okay. They don't even bother labeling the y-axis, right? Because they expect you to, everyone will be looking at the same plot, right? Because you've all been like, brainwashed thinking this is the greatest thing in the world, but, and I think the fact that it's kind of annoying to use makes you think about it, which makes it easy, makes you learn it even better, right? So if it's too easy, then then you guys will forget it, right? So this thing is so annoying. I still remember this from 2005 when I took this class, right? That was so annoying and so confusing, right? Anyway, so what's plotted here is basically that funky number, the a decibel, right, on the vertical axis as a function, well, at least they label log of f down here, right? So this has some big gain at low frequency, right? And it drops down, basically exponentially. This is on a log graph, right? Anything that's linear is actually exponential, okay? It drops off exponentially, and then it has this little peak right here, okay? What do you think this is designed to do with that little peak right there? Anyone wants to venture a guess? Why would you want a sharp peak at a particular frequency that has a, okay. Right, you want to have low gain everywhere else except for the lowest frequencies, because a lot of times you actually don't care about this. So you don't want high frequency noise, but then you want you want to pick out one frequency. Okay, so usually this is used as like a radio tuner. Okay, so your cell phone probably has one of these set to about 2.4 megahertz, and then another one set to 5 megahertz, so it has two different um, devices that will pick out the Wi-Fi signal for you. Okay, so people still use this thing. Okay, and that's how all this gets propagated forward, and we may end up using it forever just because, Alexander Graham Bell wants to talk to someone in Portugal. Okay. Okay. So that's the dot plot, and then you're gonna have a little assignment on that and the homework just to get a sense of what this looks like. Okay. Okay. It may not make a lot of sense to you the first time you plot it, but just plug in the numbers, okay? And it'll, and then as we use it more and more and more, you just get used to it. Okay. All right. Any questions about dot plot? Any opinion? I'm open to opinions about this. Okay. What I'm going to do is do a couple of analysis on AC circuits. Most of these came from your general physics class, but just to remind everyone, in that way we're all on the same page, and how resistor, capacitors, and inductors behave when you drive it with a alternating current source. Okay. So I'm going to analyze this little circuit here where there's a switch that can be opened and closed. I'm going to make a fully charged capacitor initially, and then I'm going to close the switch so that allows the current to flow through, right? The positive charge will combine with the negative charge here, right? Basically, eventually there'll be no charge left, right? Okay. Okay. And so how do we figure out how long this will take through this little resistor? Okay, because the resistor is kind of like a little constraint pipe, right? It's just letting a little bit of current through at a time, so it'll take a little bit of time for that to happen. Okay, so what I'm going to do is review. Okay, well, I have a resistor. I better write down Ohm's law for resistor. So, and since this is going to be a time-dependent thing, right, I'm going to do a lowercase thing. Voltage across a resistor is equal to what? What should I put here? A, B, C, D, E, F, G. So I have to sing all the way up to R. R, right? Okay. All right. So how do I relate? In this case, right? I know that you guys are thinking I should use this. Okay. That's a function of R. Oops, capacitor. Right. I know you guys are thinking about this. This is related to another equation, which will be simpler in this case to use, which is that the charge on the capacitor is equal to the voltage across that capacitor as a function of times the capacitance. Okay? So we're not going to use this one yet. Okay? They're actually related to each other, right? You can derive one from the other. This will be just a more direct path. Okay? All right. So I'm going to use this to solve for V as the capacitor voltage as a function of charge, right, divided by C. Okay? All right. I have a circuit that's going in a loop. What should I do? Apply which law? Kirchhoff's law, yeah. So let's say I start off here. I go across this capacitor, right? I lose, right, whatever the capacitor's voltage drop is. Okay? Now I'm here. I go across this resistor. I lose whatever the resistor voltage drop is. And now, since this switch is closed, I'm at the same point. So I'm at 0, right? Right? So plugging these guys in, right? Negative, oops, lowercase q, because they'll depend on time. Right? I'm gonna stop writing the time dependence, okay? I just assume that you guys know there's a time dependence in the lowercase letter stuff. Okay? R times I. Right? Now I need to solve this equation for something, right? Okay? Before I try to solve it, right, I know that, right, current, right, between the resistor and the capacitor is the same. How do I know that? Right? I'm going to call this IC. I'm going to call this part IR. Should there be a difference since there's only one pipe? Right? There's only one pipe, so they have to be the same. So in fact, right, then this can be changed into IC. Okay? While the current across the capacitor, right, is just how much charge is coming off that capacitor per unit time, right? That's a differential. Okay? So I can actually rewrite this equation as QC over C minus R dQC over dt. And now we end up with a differential equation. Okay? Don't worry, this is a very simple one. Okay? It's just like separate the variables and divide and then integrate both sides. Okay? We just need integration actually. We don't need differential equation. I shouldn't have said that word. I didn't say that. Okay? Okay, so let's just do this. So I'm going to put this stuff on the right-hand side. Right? R dQC over dt. Multiply both sides by dt. Divide both sides by r. So these guys cancel each other out. Okay, I have to do the same thing on the other side. Multiply this side by dt. Divide by r. Okay? So that means negative q. Oops. I'm going to do one more thing. So I save some space. I'm going to divide this side by 1 over qc also. And you're going to see why that's a good thing to do, as opposed to a crazy thing to do. Okay, so I'm doing the same thing on both sides. Okay, these cancel out. Okay, so the left-hand side is negative dt, 1 over rc, equal to dqc over qc. Right, that's all that's left. This is known as separation of variables. Everything that has to do with t, well, even r and c doesn't matter, right, because they're constants. Everything that has to do with t, I put on the left-hand side. Everything that has q's on it, I put on the right-hand side. Okay. Now, what I can do is integrate both sides, because now, right, the left-hand side only depends on one variable. The right-hand side only depends on one variable. I can integrate. Okay. What's the integral of dt? I'm sorry? Yeah. Well, technically t minus t naught. Okay. We're going to make t naught equal to 0. Okay. Okay. So therefore, right, this will be t. Well, there's still this minus 1 over rc crap here, right? Okay. What's the integral of 1 over q? Anyone remember that? What's the function that I need to use? Natural log. Right? And it's evaluated from some initial charge to some final, charge sometime later, okay? So this also simplifies because when you have log function that add and subtract is actually the same thing as dividing them, right? It's natural log of Q naught over Q as a function of time. All right, and this is some nasty transcendental equation, but then I'm going to try to get rid of the natural log at least, right? By exponentiating both sides, so they're anti-functions of each other, right? And then just do a little bit of algebra. You're going to see that Q as a function of time is going to be whatever the initial charge is, e to the minus t over rc, right? Big surprise, okay? It's some exponential decay. Hey, right? Is this n here? Okay. Yeah. Okay. So if you were to plot the amount of charge on that capacitor, right? And remember, charge is proportional to the voltage as a function of time times the capacitance, okay? That means the voltage is also some exponential decay, right? Okay. So, right, if you plot, is this right? 1 over RC. Oh, I think this is for a different problem. Let me go back up. Yeah. Yeah, so if you plot the voltage across the capacitor, you start off with some initial voltage, 10 volt, 5 volts, whatever that starting number is. It'll fall exponentially, okay? With the characteristic, okay, we're going to call this thing tau. It's the characteristic time. It's the decay time of that particular circuit. And why did they call this RC, right? It's because, right, it's what's in the denominator here, right? Okay? When t is equal to r times c, right, you have e to the minus 1, right? And e to the minus 1 is a special number because that's the decay constant, right? When something decayed by e to the minus 1, or 1 over 2.718, whatever that number is, right? That's a characteristic time because they just have to pick something, okay? It's nothing super special about it, but this is something we pick in order for everyone to talk about the same thing, okay? So for a RC circuit, okay, this tau is equal to RC, okay? In fact, if you do the unit analysis on R times C, you will end up with seconds as a unit, okay? I think we did that in general physics also, okay? Sort of neat, okay? So in the homework, actually this is going to be the plot you'll see in the homework, okay? I'm going to have you guys, instead of showing the discharge of a capacitor, I'm going to have you guys show if you have a battery and then an RC circuit, how fast would that capacitor get charged, okay? Okay, you'll end up with the same voltage as the battery, hopefully, okay? Okay, okay. But the answer is here already, but you're gonna have to, prove it yourself, okay? When it says show, it doesn't mean just write down the answer and show me the answer. It means start with basically like Ohm's law, Kirchhoff's law, and then actually derive all that stuff, okay? Okay. That's what the homework means when they say show, okay? Let's see. There's also other types of circuits that involves not just capacitors, but you can put a resistor, um, inductor together, okay? Okay. And this has a, you should think about inductor and capacitor as kind of like opposite devices, okay? So what happened is that in this circuit, right? Oops. In this circuit, right, you basically have the capacitor voltage is charging up very quickly, right? It starts off at 0 and it increases over time, okay? On this circuit, we just replace the capacitor with an inductor, right? And you can go through all the little analysis, the Kirchhoff's law, and then just, and then the voltage across a inductor, right? It's just Ij omega times the current, right? And do all that jazz, right? And what you would derive is that the voltage on that inductor instead of a growing exponential, oops, actually a growing exponential with a little limit on top, right? This is for the RC, right? If you have an RL circuit, okay, it'll be an exponential decay instead, okay? They kind of behave opposite of each other, okay? And we're going to see this. That's why you have both devices. That way you can have something that kind of causes charge to collect, and you have something that causes current to charge slower, okay? That's just the way to think about it, okay? What's more neat is actually, okay, before we move on, right? And then when you derive all this, you go through all the little math that the book will show you, right? You end up with this constant, right? Up here, let's just look at this one because that's more interesting, okay? Right, you have this constant once again. I'm going to rewrite this in a better form. V naught e to the negative t over L over R. Why did I do that? Right? Because for the RC circuit, right, the constant was R times C, right? It's whatever is underneath T, right? That's what I'm concerned with, right? So for an RL circuit, a resistor inductor circuit, the thing that's underneath T is L over R, okay? So this is the characteristic time for charging an inductor, okay? Okay, right, L over R. Sorry, yeah, okay. If you do the unit analysis here, right, the units for inductance and divided by the units for a resistor, you also end up with time, okay, which is kind of neat, okay? All right, so I'm going to try to talk about LC circuits. And this is stuff, I think we did this also in Gen Phys, but hopefully with now that you have a little bit more math, the math will not be as scary, okay? So for an LC circuit, so I'm going to replace the resistor with a capacitor here, okay? And this is going to turn into a resonator, okay? And how is it going to turn into a resonator? We're going to see how that works, okay? So I'm going to kind of go through the math quite a bit faster because it's in the textbook also, right? If we just start at this point, right, we apply Kirchhoff's law, we go over a voltage, we go over a capacitor, we go over an inductor, right? That's my application of Kirchhoff's law, right? Right? Voltage, you lose some voltage across the capacitor, you lose some voltage across the inductor, and you end up with the same point, so therefore that has to be 0, okay? So the time derivative of current is actually the second derivative of charge, right? Remember that you have charge, you take one derivative, you get current, you take another derivative, you get the second derivative of charge, okay? Right? So we're going to replace this time derivative of current with the second derivative of charge, and now it turns into a second order differential equation. Once again, I said that word I'm not supposed to say, but but you should hear what these things are actually called when other people talk about it, right? So we're not going to try to solve this. This is actually solved when we did the harmonic oscillator in General Physics 1. And harmonic oscillator behaves like sines and cosine functions, right? That's the solution to them, okay? So all we're going to do is we're going to guess, okay, that the solution has to be, some initial charge times some oscillation of cosine and plus some oscillation with sine with some amplitude between them that's characterized by these letters A's and B's. Okay, okay, okay. And then indeed, if you plug this into here and plug this into here, right, you're going to find that it does solve the equation. Okay, and it's actually a complete solution, which is sort of an interesting thing also. Okay. But what we're trying to figure out here is that, well, if we plug these two equations into 2.52, these are the exact same equation in the textbook, okay? What you will see is that, okay, the voltage that you get divided by the inductance, okay, it's going to be proportional, it's going to be equal to some constant here, right, some initial voltage divided by LC, and now LC is now an interesting number, okay? Okay. multiply by some oscillation stuff, okay, right? It's just sines and cosine just oscillating on top of each other, okay? Multiply by 1 over LC minus omega naught square, okay? Where omega naught is basically the, we're going to call that the characteristic frequency, okay? And that's going to be defined as basically 1 over square root of LC, okay? And then if you do the unit analysis of L times C, you're going to end up with units of second square. You square root it, you just end up with 1 over seconds, which is exactly the same units as angular frequency, okay? Okay, right? And this is interesting because, right, if omega naught is exactly equal to square root of LC, right, you plug this in here, this whole term goes to 0, right? There's no oscillation at all, right? And this is known as a critically damped system. You guys remember something like that? No. I mentioned this at the end of a lecture one time. That's it. Okay, critically damped system. Okay. Anyway, so this is this critically damped system now is where if you drive the signal at omega naught, if your input frequency is exactly the same as omega naught, then you're going to develop a resonance. So basically the signal gets bigger and bigger and bigger and bigger and bigger until basically, you know, whatever energy is lost is equal to the amount of energy that's being dissipated. Technically, in an ideal circuit, you can actually have infinite voltage driving stuff like this. You're just kind of storing up bigger and bigger and bigger voltage, right? But then in real life, what happened is that the capacitor is not just a capacitor. It's a capacitor that has a little resistance on it. The wire has a little bit of resistance on it. The inductor has a little bit of resistance on it. So you actually end up losing that energy, and it just eventually you'll have a large voltage, but it's not going to be infinite. Okay, you're not going to be able to do fusion with it or anything like that. Okay. Okay. So that's our resonance. Okay. And this is where the combination of inductor and capacitors are the most useful. They're basically, what's really happening is actually the charge, right, is being stored at the capacitor. And then when the charge is at the capacitor, that charge flows through the inductor, right, and it stores magnetic energy. And then the capacitor stores electric field energy, and then the two energies are actually oscillating back and forth with each other, okay? And at the right frequency, they're gonna give each other energy so that they are synchronized with each other. So whatever energy comes out, the inductor absorbs it. Whatever energy comes out of the inductor, the capacitor absorbs it, and so you don't lose energy in the system, and then you just gain more and more, and then the voltage gets bigger and bigger until basically you pop your circuit blows up, okay? Okay, so got 12 minutes. So I'm going to try to talk a little bit about the last section of the book, of the chapter, which is the Fourier analysis. I just want to give you guys a overview on why Fourier analysis is so important to electronics. I think there's like one homework problems I gave you guys just to practice a little bit, okay? So, and in the lab, you can see this if you want, but I made all this stuff kind of optional, okay? Because I know some of you guys are not taking math physics or still taking math physics, and Fourier analysis is usually like the last thing you guys cover, okay? So I just want to give you guys an idea why this AC circuit thing that we're dealing with, right? A lot of times you're going to just deal with a single frequency wave, right? And how is that useful when we're trying to, you know, send signal between cell phones and cell tower, right? Because usually those involve like millions and millions of different frequencies, okay? And how can that represent some arbitrary information that you want to send? You know, if I want to send, you know, Matthew, you know, the name Mattew, right? Is that right? There's an H in there too, right? How do I turn that information into a wave, right? That doesn't make any sense, right? So hopefully this will give you kind of a sense how waves can actually carry this type of information, okay? Because actually any periodic function, we're going to call that f of t, okay, can be represented as a combination of sine and cosine waves, okay? A little example up here where this is known as a square wave, so it's basically 1 volt for some time it drops to -1, sometime it goes up back up 1 volt. It's kind of like a little up down up down up down up down. Okay, right? This function can actually be represented by a bunch of sine functions. So this is sine of omega t. Okay, the green one is sine of omega t plus some constant times sine of 2 times omega t. Okay, and then the purple one is the same thing, but then now you add sine of 3 times omega t. Okay, and then the blue one is you add sine of 4 times omega t. So you're adding more and more higher frequencies of sine wave on top of each other in order to make an interference pattern that gives you a square wave. Okay, and I'm not going to go through these other ones. You can represent a sawtooth function with this. And triangular wave is actually kind of simple because like the first sine of omega t is kind of already like a triangle, right? You can represent a semicircle with this. Okay, you can represent like any type of shape with this. Okay, and then if you can represent any shape with your sine and cosine function, that means you can actually draw whatever you want, right? That means you can represent Matthew or Alan, whatever your name is, right? And represent those in terms of waves. By combining multiple waves together, you can actually send information using these AC circuits. Okay. So the math here gets a little funky. Don't take notes on this, okay? It's all in the textbook anyway. If you're really into this, feel free to dive into this chapter, this section, and go through everything that the book's talking about. So mathematically, this arbitrary function that we can write, the function for Matthew or function for Uriel, something like that, whatever information you want to send across, can be represented by this definition, okay, where is some sum of some cosine functions and some sine functions with some what's called coefficients in front of them to basically weight them so that you're in this example here up here, right, the omega t has a big amplitude, but you want to add just a little bit of 4 times omega t on top of it in order to make it straighter and straighter and straighter. Okay, that allows you to kind of weight these functions so that you're not adding them equally. Okay, and by definition, there's just going to be some constant in front, just so you can shift the function up and down if you want. Okay, all right, and then to calculate this is basically this doesn't look like a Fourier transform yet, but it is basically a Fourier transform. To figure out what these coefficients are, you basically do some fancy integral of that function. Okay, and this is stuff you can just chug and play, right? You just type in your calculator or your Mathematica or Python. It'll do all this math for you. Okay. Don't worry too much about actually doing this. Okay. So instead of representing things as both sines and cosine, and I say I don't like sines, I'm just gonna not worry about sine at all, right? Sines and cosines are actually just related to each other through a 90-degree phase shift, right? They're the same function, except they're just shifted. So you can actually, instead of having sines and cosine, you can represent it as just a cosine function that possibly have a phase shift. Okay, all right. I know this is just a lot of things that you guys will learn in math physics at some point. Okay, and then if you want to compute these coefficients, you can still do the same thing by doing this fancy integral by just basically taking the square root of these those coefficients that you calculated before, and then the phase shift has to be calculated as this inverse tangent function. What we're going to do is I just want to show you guys some example of what it looks like. Okay, from what we learned Monday, right? Okay. Instead of writing cosine functions and dealing with trying to remember what trig functions are, the trig identities are, right? We can just take the real part of an exponential, right? E to the ij omega t. Just ignore this n for now, right? Remember that was familiar from Monday, right? We just take the real part of this, right? And we can do the same thing, right? We're just doing this is basically the cosine part. Okay. All right. In this case, what happened is that, well, if you want to compute these coefficients, now you take your function, you multiply it by e to the ij omega t, all right, and you do an integral. Okay. And this is actually what the Fourier transform is, if you ever run into this in the future. Okay? The Fourier transform is just taking your function, multiplying it by some other, well, in the Fourier transform, it's actually e to the ij omega t. Okay? You can do other types of transform if you want. It's just changing your variable as a function of t to a function of omega, actually. Right? Because once you integrate as a function of t, all the t's goes away, right? You evaluate from t minus half the period to the full to plus half the period. This actually goes away. This is actually a function of omega. Okay, but that's not too important. Okay, so the idea is that you can do this for any arbitrary function. You do all this fancy math with it, and then so therefore you can represent it as some combination of cosine function. Okay, in this case e to the ij omega t. Okay, some periodic function. Okay. All right. The best example in the book is the square wave. Square wave. Okay. Remember the square wave is that it's just it starts off as -1, and then when it's 1, and then it goes to -1, 1, -1. It just goes up and down, up and down, up and down. It's a pretty boring function, right? Okay. If you plug this function f of t into this equation here, okay, you can do this, right? Because what happened is that when t is negative on the negative side, you just put -1 here, right? When t is positive, you just put 1 here, right? And you can integrate e to the ij omega t, right? The integral of that, right, is just eij omega t, right? And then you just pop down the constants, right? ej omega t, and you just pop down the constants, which is negative, right? That's the integral, right? So you can do these integrals pretty easily. Okay? Since this is a j, right? And remember, this is cosine of omega n t plus j sine of omega n t, right? So there's a j in front. That means is the cosine the real part or sine the real part of this function? I'm sorry? The cosine is real? Right, the sine, right? Because you multiply this out, right? Now this is the imaginary part, right? So all of this function, right, this turns into 1 actually, because j squared is -1, -1 times -1 is 1, right? So all these functions, right, all these coefficients are actually sine functions, okay? So what you do is you plug this into here, plug these n's, oops, into here, right? Okay, and that's basically how big you want these functions to be. Okay, you plug all this stuff in here. You can calculate. Well, you wouldn't do it yourself. You just type it in Mathematica, it'll do it for you. Okay. What happened is that if you plot this, okay, let's say I only plot the first term, right? That means I'm only plotting, right? Um, let's call this big F, right? That's a function of t. Is equal to, what is this up here? 1/2, right? And then this first one is pi over 4 sine of 2 pi t over t times sine of, well, omega 1 is going to be, I think, 1 over, is 2 pi over t, right, times t, okay? If you plot that, what you end up with is this dashed line here, okay, right? Not really close to the, it's not that close to the, what's this called? What's the function called? The purple one? Square wave, yeah, remember, okay? But now if you plot basically the sum of, the first term and the second term, actually the third term, okay? And since this is an odd function, actually only the odd coefficients are non-zero. All the n equals to 2 is actually equal to 0. N equals to 4 is equal to 0. And that's because this is an odd function. If you reflect it with um, the y-axis, it'll just be negative of itself, right? Okay. So you add up the first term and the third term, then you get something that's closer to a square wave, right? If you do it to the to the to the to n equals to 5, then you get closer. N equals 7, you get closer. 9, you get even closer. You get up to 11. That's pretty darn close to a square wave. And that's actually what your function generator is doing all the time. When you tell it to make a square wave, it's actually adding a bunch of sine waves together, adding a bunch of cosine waves together. Okay? Okay. So I just want to get you the idea that, right, these sines and cosine functions that you guys are playing with on your oscilloscopes, right? If you have just one wave, it doesn't do a lot, right? But if you have like, 10 different wavelength frequencies, right? You can actually represent arbitrary functions with it, so you can send information back and forth between things, okay? The book also does this little rolling sine function, so I won't go through that, so you can look at that yourself, okay? Um, Besides from representing signals by just combinations of sines and cosines, you can also filter them, meaning if you take this term, right? If you take this little function, I'm just going to knock out the n equals to 5 term, okay? And that will change the function, right? And so you're filtering on that one particular frequency, basically 5 times whatever omega naught is, right? You're filtering on that one particular frequency, and that'll change the function that'll come out also. So you can actually filter in or filter out stuff, okay? By picking out particular wave frequencies, okay? So the example that I just want to show you guys the picture of, if you right, if you have this little rolling function here, right? If you take out the n equal to 0 term, right, then it actually shifts it. Remember, n equals to 0, n equal to 0, right? Where is it? It's a constant term, right? It shifts the function up and down, okay? Right? And then, right, as you take out more and more terms, right? So originally, so you can't see this, but there's a blue behind this. Originally, they're pretty good representation of the function, right? When you take it out, right, then it shifts it down. Now you're not getting the height right, okay? Right? If you take out more and more terms, wait, where did it go? If you take out more and more terms, the function kind of gets even more different from each other, okay? So what you can do is by filtering out, by basically subtracting certain frequencies out of your signal, you can make a little bumpy curve into a flat curve, right? So that's how you filter out stuff, okay? So that's a way to reduce the gain of something, and then we're going to see how that works next chapter when we talk about filtering circuits and how we play around with this in the terms of